On Christmas Day 2021, a rocket lifted off from the coast of South America. Inside it was a machine 25 years in the making. The most expensive scientific instrument ever built. A telescope so powerful it can see light from the first stars to ever exist. Its name is the James Webb Space Telescope, and what it is finding is forcing scientists to rewrite the textbooks. Not update them, rewrite them. In its first 3 years of operation, Webb has discovered galaxies that shouldn't exist, atmospheres on planets that weren't supposed to have them, structures at the edge of the universe that contradict models physicists have defended for decades. This is not incremental progress. This is a fundamental challenge to how we understand the universe. This is what Webb is finding, and why it changes everything. To truly grasp why the James Webb Space Telescope's discoveries are sending shockwaves through the scientific community, you first need to understand the incredible machine itself and what it can actually do. It's a story not just of new technology, but of a new way of seeing the universe. For more than 3 decades, our premier eye on the cosmos was the Hubble Space Telescope. Launched in 1990, it orbited just a few hundred kilometers above Earth, a sentinel in the dark. Hubble was revolutionary. It peered into the void and showed us galaxies billions of light years away, each a city of stars, more numerous than we had ever imagined. It gave us the iconic deep field images, revealing a universe teeming with structure and history. By observing these distant galaxies, it provided crucial evidence that confirmed the expansion of the universe, a concept that underpins all of modern cosmology. It captured the birth and death of stars, photographed colliding galaxies, and analyzed the atmospheres of planets beyond our solar system. Without a doubt, Hubble changed astronomy forever, transforming it from a science of speculation into one of direct observation. But Webb is not Hubble's replacement. It's not just a bigger, better version of the same thing. It is something fundamentally different, a successor designed to answer the questions that Hubble's own discoveries raised. The key difference lies in the kind of light they see. Hubble sees primarily in visible and ultraviolet light, the same light our eyes can detect, just with far greater sensitivity. Webb, on the other hand, is an infrared telescope. It is designed to see the universe in a light that is invisible to the human eye. That distinction sounds technical, almost trivial, but its implications are nothing short of extraordinary. Seeing in infrared isn't just a neat trick, it's like unlocking a secret, hidden layer of the cosmos. Here is why infrared matters. The universe is expanding. It has been since the Big Bang. This isn't like an explosion in space, it's the expansion of space itself. As it expands, light from distant objects traveling through that space gets stretched. Think of a wave drawn on a rubber band. As you stretch the band, the wave gets longer. Light behaves the same way. This stretched light shifts toward the red end of the spectrum, a phenomenon called redshift. The further away an object is, the faster it appears to be receding from us, and the more its light is stretched. Now consider the oldest objects in the universe, the very first galaxies, the first generation of stars to ignite after the Big Bang. They are so incredibly far away that their light has been traveling for over 13.5 billion years to reach us. Over that immense journey, their light has been stretched so much that it has shifted completely out of the visible spectrum and falls entirely in the infrared range. To Hubble, these first lights were simply invisible. It was like trying to hear a sound that was pitched too low for our ears. But Webb can see them. It was built specifically to capture this ancient, red-shifted light, allowing us to witness the cosmic dawn for the very first time. To capture such faint, distant light, Webb needs 2 things: a giant mirror and extreme cold. First, the mirror. Webb's primary mirror is a breathtaking 6.5 meters across, composed of 18 gold-coated beryllium hexagons. For comparison, Hubble's mirror is a solid 2.4 meters. This gives Webb a light collecting area more than 7 times larger than Hubble's. Think of it as a bigger bucket for catching photons. The bigger the bucket, the fainter the objects you can see, and the faster you can see them. Second, the cold. Infrared is essentially heat radiation. To detect the faint heat signatures of objects at the edge of the observable universe, the telescope itself must be incredibly cold. Otherwise, its own heat would blind its instruments. Webb operates at a chilling -233 degrees Celsius, colder than the surface of Pluto. This is achieved with a massive 5-layer sun shield, the size of a tennis court, which constantly blocks heat from the sun, Earth, and Moon. To maintain this perfect, cold, dark environment, it couldn't stay in Earth's orbit like Hubble. Instead, it launched to a unique gravitational balance point 1.5 million kilometers from Earth, called the second Lagrange point, or L2. Here, it can keep its back to the Sun, Earth, and Moon simultaneously, far enough from their interference to see in perfect, uninterrupted darkness. It is an undisputed masterpiece of engineering, pushed to the very limits of what is possible. And what it saw when it finally opened its golden eye to the cosmos has not stopped surprising, challenging, and thrilling scientists since. For decades, our understanding of the cosmos has been guided by a single, powerful framework, the Standard Model of Cosmology. It's our grand narrative of the universe, a story that begins with the Big Bang and explains, with remarkable success, how everything we see came to be. This model is built on pillars like dark matter and dark energy, and it has correctly predicted countless observations, from the afterglow of creation to the distribution of galaxies across billions of light-years. It is the bedrock of modern astrophysics, and this trusted model makes a very specific, very clear prediction about our cosmic origins. It says the early universe was simple, almost featureless. In the immediate aftermath of the Big Bang, the cosmos was a searingly hot, dense soup of particles. As it expanded and cooled, matter was spread with incredible uniformity across the vastness of space. We see the proof of this in the cosmic microwave background, the faint light from that era, which is almost perfectly even in every direction we look. But it was only even. Tiny, quantum-scale fluctuations in density, infinitesimally small ripples in the fabric of space-time, were the only imperfections. According to the Standard Model, these tiny seeds of structure were where the story of galaxies began. The process of building the first galaxies, therefore, should have been painstakingly slow. Gravity, the universe's master architect, had to work patiently with what little it had. Over immense timescales, it would gently pull matter from the surrounding voids toward those slightly denser regions. This is a process known as hierarchical formation. Small things form first. Small, wispy clouds of gas and dark matter would coalesce into the first dwarf galaxies. Then, over hundreds of millions of years, these smaller structures would merge, colliding and combining to build, piece by piece, the larger, more massive galaxies we know today. Based on this model, the timeline was clear. The first truly massive, fully formed galaxies, complex systems with billions of stars and organized structures, should not appear until the universe was at least 1 billion years old. Before that, we expected to see only their small, faint, and chaotic ancestors. Then, the James Webb Space Telescope opened its eyes, and it found them at just 300 million years after the Big Bang, a mere cosmic heartbeat after creation. These weren't the small, primitive proto-galaxies our models predicted. They weren't the faint, disorganized building blocks we were searching for. They were massive, fully structured galaxies. Some appeared to be as mature as our own Milky Way. They contained billions of stars that had already formed, a process that should have taken far, far longer. They were already organized into complex structures like disks and bulges. They were impossibly already old. It was like finding a fully grown redwood tree in a greenhouse where you'd only just planted the seeds a week ago. In July 2022, a team of researchers identified 6 of these shocking objects in Webb's very first deep-field images. They were so unexpected, so contrary to all predictions, that the team struggled to believe their own data. They checked and rechecked their work, looking for any error that could explain away these cosmic anomalies. But the data held firm. In their initial paper, they gave these galaxies an informal, dramatic name. They called them universe breakers. One of them, a faint red smudge designated JDS GSZ140, was later confirmed in 2024 through rigorous spectroscopic analysis as the most distant galaxy ever observed. The light we see from it today began its journey when the universe was just 290 million years old, less than 2% of its current age. And it was already enormous, spanning over 1,600 light-years across and shining with the light of 1 billion suns. It was already producing new stars at a ferocious rate, a pace that our models said shouldn't have been possible that early, when the supply of cosmic gas was still supposed to be diffuse and unorganized. The discovery sent shockwaves through the astronomical community. Catherine Whittaker, an astrophysicist at the University of Massachusetts and one of the researchers who identified the original 6 galaxies, was direct about the profound implications. She said the findings could require fundamental changes to the standard model of cosmology. This isn't about small tweaks or minor refinements to the existing theory. This points toward fundamental changes. Somehow, the universe formed complex structures much faster than our most successful models said was possible. The cosmic seeds of creation sprouted and grew at a speed that defies our explanation. We don't yet know why. Perhaps the first stars were far more massive and efficient than we thought. Perhaps dark matter behaves in unexpected ways. Or perhaps there's a new, unknown force at play in the early cosmos. We don't yet know what this means for everything else we thought we understood about our universe. The one thing we know for certain is that the story of our cosmos has just become far more mysterious. The second major area where the James Webb Space Telescope is rewriting the rules of astronomy is, in a cosmic sense, closer to home. Relatively speaking, of course. We're talking about exoplanets. These are planets orbiting stars other than our Sun, scattered throughout the Milky Way galaxy and beyond. For millennia, they were purely the stuff of speculation, a philosophical question. Do other worlds exist? Then, in the 1990s, we found the first one. The floodgates opened. Missions like the Kepler Space Telescope and TESS began a systematic census of our stellar neighborhood. Today, we have confirmed more than 5,500 of them, with thousands more candidates waiting in the wings. Each one a new world, a new possibility. But for most of the history of exoplanet science, our knowledge was frustratingly limited. We could detect them, often indirectly, by observing the subtle dimming of a star as a planet passed in front of it. This is the transit method. From that dip in starlight, we could measure their size. By timing their orbits, we could calculate their distance from their star. We could build a catalog of worlds, hot Jupiters, super-Earths, mini-Neptunes. But we could not look at them directly. They are unimaginably faint, completely washed out by the glare of their parent stars. It was like trying to spot a firefly next to a searchlight from miles away. Because we couldn't see them, we could not examine their atmospheres. We could not perform the most fundamental analysis, spectroscopy, the science of decoding light to reveal its chemical composition. And so, we could not ask the question that matters most, the question that drives our search for worlds beyond our own. Is there anything in that atmosphere that shouldn't be there? Is there a chemical fingerprint, a biosignature, that could only be produced by life? Webb changed that. Its incredible sensitivity and infrared vision allow it to do what was once impossible. As an exoplanet transits its star, Webb can capture the minuscule amount of starlight that filters the planet's atmosphere. The gases in that atmosphere absorb specific wavelengths of light, leaving a barcode-like pattern imprinted on the starlight. By reading that barcode, Webb can tell us what the air on another world is made of. In 2023, Webb provided a stunning demonstration of this power. It confirmed the detection of carbon dioxide in the atmosphere of WASP-39b, a puffy, hot gas giant orbiting a star 700 light-years away. It was the first time carbon dioxide had ever been definitively detected in the atmosphere of a planet outside our solar system, a landmark moment, proving the technique worked flawlessly. Then, Webb turned its attention to a far more tantalizing target. It turned its golden eye to K2-18b. This is a planet 120 light-years away, in the constellation Leo. It's what's known as a sub-Neptune, larger than Earth, but smaller than Neptune. Crucially, it orbits within the habitable zone of its star, the region where temperatures could allow for liquid water to exist on a planet's surface. In fact, previous observations had suggested K2-18b might be a Hycean world, a planet that may have a liquid water ocean beneath a thick, hydrogen-rich atmosphere, a completely new type of environment, unlike anything in our solar system. In the atmosphere of K2-18b, Webb detected methane and carbon dioxide. But it also found a tentative hint of something else, a molecule called dimethyl sulfide, or DMS. This was an electrifying discovery, because on Earth, dimethyl sulfide is produced by only one known process in any significant quantity: marine phytoplankton, living organisms. Microscopic life in our oceans releases this gas, which then enters the atmosphere. Finding it on a potential ocean world 120 light-years away is profound. The researchers who made the discovery were extremely careful. Science demands caution, especially when the stakes are this high. They stated clearly that the signal was not a definitive detection and needed further confirmation with more observation time. They said it could have an unknown, non-biological source. Perhaps some strange chemical reaction, unique to the high-pressure, hydrogen-rich atmosphere of a Hycean world, could produce it without life. They did not claim to have found life. That would be a monumental and premature leap. But they said the signal was there, tantalizing, persistent in the data, and that if confirmed, it would be the first detection of a potential biosignature on another world. The first hint that we are not alone. We are waiting for that confirmation. Webb is scheduled to look again, to stare longer, to gather more photons from that distant world. The data is still being analyzed. The scientific process is slow, methodical, and rigorous. It must be. And the universe is not saying yes yet. It holds its secrets close. But for the first time in human history, thanks to this incredible machine, it is not saying no. There is a connection between Webb's discoveries and the Fermi paradox that most coverage misses. In the last video, we asked where everybody is. We asked why the universe is silent. We talked about the great filter. Webb is making that question more urgent, not less. Here is why. The Drake equation, the formula for estimating the number of communicating civilizations in our galaxy, depends on how common life-supporting conditions are. Every time Webb confirms water on a planet, every time it detects organic chemistry in a distant atmosphere, every time it finds that the conditions for life are more widespread than we thought, it pushes the number of potential civilizations upward. And yet the silence continues. Webb is the most powerful search instrument in human history. It is not designed to detect alien signals, but it is designed to detect the chemical signatures of life. And so far, across every planet it has examined in detail. The atmospheres are interesting. The chemistry is complex, but nothing is conclusive. The more Webb finds, the more habitable zones, the more water, the more organic molecules, the more the silence should bother us. Because the universe keeps passing the habitability test, and nobody is home. The James Webb Space Telescope has been operating for less than 4 years. It is designed to last at least 20. In 4 years it has found galaxies that contradict the standard model of cosmology, detected carbon dioxide on a planet outside our solar system for the first time, identified a potential biosignature on a planet 120 light-years away, mapped the atmospheres of planets in unprecedented detail, captured images of the universe that no human instrument has ever seen before. We are at the beginning of what Webb will show us, not the end. The scientists who built it spent 25 years waiting, advocating for funding, defending the project through cancellations and delays and budget cuts, because they believed that if we could see further, we would find something that mattered. They were right. They just didn't know how much it would change. What Webb is doing is not filling in details on a picture we already understood. It is showing us that the picture was wrong, that the universe is older in some places than our models allow, that life's building blocks are more common than we knew, that the cosmos has been doing things we didn't expect, long before we were here to watch. We have only just opened our eyes. Stay tuned to the void frequency. The universe has been broadcasting for 13.8 billion years. We're just finally learning to listen.